We've just been investigating the nature of waves, and we finished off looking at refraction. Now we're going to investigate in more detail refraction. This is a key aspect of wave nature. To do that, you're going to need these things here. An ice cream container, a light one, white or a light colour, some cardboard, ruler, a permanent marker of some sort, scissors, pencil, a flexible tape, not sewing tape or some sort of tape that's flexible. Your solutions that you made way back in the first topic, salinity, if you've still got them, if you haven't, you're going to need salt, and you're going to need to make them up again, and a jug of fresh water. Okay, so what we're going to do, if we're looking at refraction, we're looking at how waves bend as they move from one medium to another. This medium out here, air, is going to be the first medium, and the second medium, some form of water, is going to be in there. But we want to get a handle on just how much bend is happening. So to do that, we need something that's going to sight down into our container. We're going to mark some marks on the container, so again we've got some sort of scale of how much bend is, and using your flexible tape, mark in centimetres along the bottom of the container. The first mark is going to be right on that edge and corner there. I'm going to use every 5 millimetres. That'll give me a pretty good scale. I don't have to be too fussy about that. But again, you know, if you're not so steady-handed and your eyes are not as good as mine with glasses on, then you will need to get somebody in the household who is good at this stuff. Probably we want to go past the halfway mark, I would suggest. So we're looking probably about 9 or 10 centimetres from the edge. That should do us. Okay, but it would be handy to actually number them because we want to count them. So we're just going to go 1, 2, 3, done. Scale. So to make sure that our head is looking in the same angle each time, we need something to rest it on and have a sighting angle. And to do that, a piece of cardboard which you can rest your chin on, and I just close one eye. If you can't do that, put a patch over your glasses or something, and then hold your one eye there, and you want to be looking down at our number 1 right at the start, and you sight down the ruler over the edge, the front edge of that container, right at that first line, so that you're looking right down the edge of the ruler, right at the first line, with your chin resting on that. Hold the ruler on the cardboard, draw with pencil down that line, and just cut that sight line out. Pretty quick, pretty easy. But this will make sure that when we reset our medium, our container, we're looking down that sight line at same point. Next thing is, we're going to see just what that water does to the refraction, the bending of the light. So I've got my litre of fresh water here, I'm looking down, I've got my chin on my sight line, I'm looking down, I can just see number 1, and as I put the water in, lo and behold, as if by magic, I now see number 2, I see number 3, I see number 4, I see number 5, and if I look carefully, I now can see right down to 1, 2, 3, 4, 5, 6, 7. I can see right down to 7. And you can see for yourself, as we put that different medium in, that the light must be travelling along through the air down my sight line, but then bending so that I can now see further down my scale on the bottom. In actual fact, the light waves are travelling from the bottom of the container up through the water, refracting as they enter the air, and then heading to our eye. I mean, that's how we are seeing that bottom of the container and how it changes. We're going to repeat with no water, with 0 parts per thousand, with 35 parts per thousand, and with 50 parts per thousand, and just compare very carefully how much bend there is. There doesn't seem to be a lot of difference, but if we're precise and careful with our measurements, and also if we double our measurements. So what I've done here is put 2 litres in, and so the surface of the water is much deeper and it exaggerates a little bit more. Care with accuracy and precision in the layout of the geometry and measurements will allow us to use algebra and trigonometry to calculate the relative refractive index. You will need accurate and precise measurements of A and B for both angle I and angle R. Okay, so light has the wave property of refraction. We can also use that to measure salinity. Going back to our first topic, an instrument that does that is actually called a refractometer. And the way it works is that the sample of water is placed upon the stage and the light travels through that water and the angle of refraction is converted into the scale. And I hold that up to the bright light and I focus it with my eye, and where the bottom of the blue is, basically, is the reading of salinity. And here's what it looks like. On the left we have specific gravity, on the right we have salinity in parts per thousand, and you've just seen pure water, and this is seawater. The greater refraction of the denser seawater is translated into a visual scale where we can see the salinity. Could visualise this in our own experiment when the freshwater mark is compared here, just near the 14 with the 35 parts per thousand. When it's measured along the bottom, it's only about a 2 millimetre difference, and that's only about a degree difference for the angle for refraction.